This episode is brought to you by Brilliant. If two cars collide head-on, each moving at just 24 kilometers an hour or about 15 miles an hour, a speed just two-thirds that of an Olympic sprinter, somewhere around 35 Gs of force will be experienced by both drivers in the front-end collision, given that they're both wearing seatbelts. Assuming 80 kilograms or 176-pound drivers, their seatbelts would have reduced the average force experienced by their bodies to around 27,000 newtons, or about the equivalent of around 6,000 pounds of mass being pressed against the drivers. While traumatic, these forces are generally not deadly and are a direct result of seatbelts spreading the deceleration of their bodies over time. Without the force-reducing effect of seatbelts, the drivers would have experienced an average force almost 4 to 5 times higher as their bodies decelerate upon impact with the vehicle's interior. With the threshold for traumatic brain injury being just 50 Gs, it becomes clear how even extremely low-speed, unprotected collisions can become catastrophic. Seatbelts work by increasing the time it takes the occupant to reduce their speed from the vehicle's impact velocity down to zero in a collision, all while spreading it along the most robust parts of the human body. This effectively reduces the average deceleration force experienced by the occupant. While seatbelts are highly effective, they're limited by the amount of stretch they can safely provide. Since the inception of the mass-produced automobile, the concept for a device that could further enhance the amount of force-reducing effect produced by restraints have existed. However, it would take a combination of the semiconductor revolution mixed with a byproduct technology of the space race to bring the long-sought-after idea into fruition with the commercial advent of the airbag. An airbag, in its most elemental form, is an automotive safety restraint system designed to inflate a cushioning bag extremely quickly, then rapidly deflate it in a controlled manner during a collision. They're considered a passive restraint system because, unlike seatbelts, they require no interaction by the occupant for their operation. Much like seatbelts, they also lower the exposure to injury by increasing the interval of time the occupant is exposed to deceleration and by spreading the force over a larger area of the body. However, they offer this protection to the occupant in regions of the interior that are beyond the reach of traditional seatbelts. They can prevent the occupant from striking interior objects, such as the steering wheel or window, and from various angles of impact. An airbag system is fundamentally composed of one or more inflation mechanisms, located primarily within the steering wheel for the driver and the upper dashboard for the front passenger. Additional mechanisms may also be embedded within the lower dashboard, doors, pillars, roof structure, the seats, and even the seatbelts. These mechanisms are concealed within the vehicle's trim behind plastic flat panels that are designed to tear open under the force of the bag's inflation. These inflation mechanisms are controlled by a centralized system that continuously monitors for impact events using as little as 1 to dozens of sensors, depending on the system's sophistication. Once the system detects an impact, one or several inflation mechanisms are pyrotechnically triggered by an electrical signal, causing a gas-generating propellant to be ignited, rapidly inflating a bag that is folded within each inflation mechanism. As the occupant collides with the bag, the gas escapes in a controlled manner through small vent holes, cushioning their deceleration. The airbag's volume and the size of the vents are specifically designed to provide the largest increase in deceleration time possible for that specific vehicle and its location within it. While simple in concept, the difference between an airbag's deployment protecting an occupant and causing traumatic or even deadly injuries comes down to precise millisecond timing of its operation. Most two-vehicle collisions are between 70 to 150 milliseconds in duration and can be divided into 3 stages. First comes initial contact, where the vehicles first touch each other. Next comes maximum engagement, where the peak deformation and intrusion of the vehicles occur. And finally, separation occurs as the vehicles pull away from each other and come to rest. For an airbag system to not just be effective, but also not cause more harm, its control system must evaluate all forces in play and initiate a deployment strategy well before the maximum engagement stage occurs. This is typically accomplished within 15 to 50 milliseconds from detection of the initial contact. This incredibly narrow window to act within the first 1/3 of the entire collision duration is due to the airbags needing to deploy before the occupant contacts any portion of the vehicle's interior as it crushes, and before the limits of the seatbelt stretch are reached. The airbag's inflation must also be timed so that it's fully inflated before the occupant engages with it to minimize trauma from the inflation process itself. While the idea for using an air-filled cushion for vehicle and aviation safety dates back to the 1920s, the first patents for a system that automatically inflates as a result of sudden deceleration were independently issued just 3 months apart in 1953 to American John W. Hetrick and German engineer Walter Linderer. Both systems were based on a store of compressed air that would inflate the airbag using mechanical trigger valves. Hetrick's system could be triggered in one of 3 ways: by a bumper contact valve, a mass spring deceleration detecting valve, or manually by the driver. By the 1960s, practical airbag systems for vehicles were being explored by the major manufacturers, and from this decade of research, it was determined that compressed air systems were far too slow reacting to be effective. Furthermore, the mass spring valve proved to be dangerously inaccurate for detecting collisions. These flaws made the mechanical compressed airbag system completely unsuitable for commercial adoption. In 1967, Alan K. Breed would make a breakthrough that finally made airbags commercially viable with the development of the ball-and-tube electromechanical crash detection sensor. Breed's sensor worked by holding a steel ball in a resting position using a magnet. When a collision occurs, the ball is separated from the magnet, moving forward to electrical contacts and closing the trigger circuit. Because this ball required a significant change in acceleration to break away from the magnet when compared to just a change in velocity with a mass spring, the ball-and-tube sensor is far more accurate in detecting a collision. The entire action of the trigger mechanism is also sealed, self-contained, and can activate in under 15 milliseconds, making it an ideal candidate for commercial use. In addition to crash sensing, Breed pioneered the use of a gas generator as a method for rapidly inflating an airbag. A gas generator creates gas by a chemical reaction, either from a solid or liquid source, and it's ideal for when storing a pressurized gas is impractical. Gas generators are derived from the devices used in rockets to generate large quantities of gas to power the turbopumps within their engines. Their ease of packaging and simplicity would make them ideal for other aerospace and military applications, such as aircraft emergency power sources, jet engine start systems, and even as torpedo power sources. From this, Breed devised an inflation mechanism that used just 30 to 150 grams of the solid fuel sodium azide as a gas-generating agent for airbags. Packaged behind a folded neoprene-coated nylon bag, the sodium azide charge would be ignited by a resistive wire that would heat up to over 300 degrees Celsius or about 572 degrees Fahrenheit within 2 milliseconds when a current was applied to it. The sodium azide would then exothermically decompose rapidly to sodium and nitrogen, fully inflating the airbag with the resultant gas within just 60 to 80 milliseconds. While the nitrogen produced is inert, the resultant sodium metals within the generated gas proved to be hazardous and an irritant, so additional additives such as potassium nitrate and silica would be added to neutralize the sodium, converting it to silicate glass within the reaction. By 1965, automobile accidents had become the leading cause of death of Americans under the age of 44. This fact had been largely ignored by both the government and manufacturers until public attention on the matter was brought on by a combination of litigation, recalls, and the popularity of Ralph Nader's damning journalistic expose on the automotive industry. Extensive congressional automobile safety hearings the following year, chaired by Senator Robert Kennedy, grabbed the spotlight, and by 1966, President Lyndon Johnson would sign legislation that created a federal agency to regulate automobile safety, now known as the National Highway Traffic Safety Administration, or NHTSA. Any car sold in the United States must now be certified to meet the Federal Motor Vehicle Safety Standard, or FMVSS, a comprehensive set of regulations on vehicle design, construction, and performance. Over the next decade, FMVSS mandates would usher in a new age of automotive safety with requirements for life-saving shoulder lap belts, collapsible steering columns, stronger door latches, shatterproof windshields, and safer dashboards. Empowered by its success, the NHTSA began to prepare for a second wave of mandates during the 1970s, specifically targeting a push for new safety technologies, with the airbag being a prime technology for regulatory compliance. Driven by this initiative, the first mass-produced vehicle to have an airbag system was introduced on a government-purchased test fleet of 1,000 Chevrolet Impalas in 1973. Called the Air Cushion Restraint System, or ACRS, General Motors employed impact sensors mounted in the vehicle's front bumper in order to deploy the airbags embedded in the steering wheel for the driver and in the dashboard for the passenger. The passenger side trigger mechanism had a novel dual-stage system that employed one of two inflation forces based on the severity of the impact. Due to the success of the government-purchased fleet, GM decided to offer ACRS as an option for full-size Cadillacs, Oldsmobiles, and Buicks for the 1974 model year. Despite its technical success, ACRS was not a popular option, and by 1977, ACRS was discontinued by GM. During this period, the industry began to push back against the NHTSA's second wave of regulation through extensive lobbying efforts, with airbags being cited as an infeasible technology. By 1984, the NHTSA would reach a compromise with the industry, and with this, agreeing to the introduction of a passive restraint system mandate for all new vehicles produced in the US beginning on April 1, 1989. Manufacturers now had two options, either an automatic seatbelt system or the airbag. This requirement directly resulted in the US leading the commercialization of airbags. During the 1980s in Europe and Japan, airbags were starting to be offered on higher-end sedans. Porsche would become the first car to have driver and passenger airbags as standard equipment with the 1987 944 Turbo. The next year, Chrysler would become the first US manufacturer to fit a driver's side airbag as standard equipment within their entire product line, and even began promoting the life-saving effectiveness of airbags in commercials. With airbag systems now guided by regulations, the 1980s saw the shift of the industry's view of airbags as a primary safety system to one designated as a supplemental restraint system, or SRS, or the less common designation of supplemental inflation restraints, or SIR. By the mid-1990s, regulatory requirements made airbags a standard option in most cars sold in the US, directly leading to the technology being adopted by both European and Japanese manufacturers throughout most of their product range. In 1998, the FMVSS would extend the airbag mandate to light trucks, and by the turn of the century, almost every new vehicle produced contained an airbag system, with most offering both driver and passenger protection. This proliferation led to the development of a new generation of airbag systems during the 1990s that overcame the flaws of earlier systems through the use of recent breakthroughs in the semiconductor industry. At the heart of this evolution was the transition from electromechanical triggers to MEMS accelerometers. MEMS, or microelectronic mechanical systems, are microscopic mechanical elements that are embedded into integrated circuits. They can be designed to perform a broad range of environmental sensing, though accelerometers are their most popular application. To learn more about how this revolutionary technology works and how it's applied to motion sensing as well as other less obvious applications, check out the video The World of Microscopic Machines. MEMS accelerometers were small, durable, extremely reliable, less costly, and easily embedded throughout a vehicle. But what made them so groundbreaking was the signal they produced and how it was used. The electronic control units that formed the backbone of airbag systems, called the Airbag Control Unit, or ACU, would now become an embedded computer, relying on a fusion of MEMS sensor data and other vehicle inputs to employ algorithms that could now manage a larger spectrum of collision types and inflation response strategies. In an impact event, the kinematics of the collision can be quantified by several orders of motion measurements. At the bottom is the displacement of the vehicle in distance. Then above this is the vehicle's displacement over time, or its velocity. From this, the next order of measurement, the change in the vehicle's velocity over time, or its acceleration, is determined. And finally, the next order of motion measurement is called jerk, which is the rate of change of acceleration over time. On the early mass spring systems, acceleration was used as a trigger. This proved to be dangerously inaccurate, as the trigger acceleration could easily overlap with the dynamics found on a normal vehicle's operation. With the advent of the ball and tube sensor, the nature of the magnetic force on the ball created a pseudo-jerk-based trigger, which is far more accurate for impact detection. However, this trigger threshold was limited to the specific force profile that was physically designed into the mechanism. Furthermore, mechanical-based sensors were limited to measuring forces in the direction of their orientation. In contrast, MEMS-based ACUs continuously sample multiple MEMS accelerometers, perpetually searching for an algorithmic match to force profiles of acceleration and jerk stored within its memory. Once one or more acceleration sensor signals trigger a pattern match, the ACU then combines other sensor inputs such as brake pressure, wheel speed, vehicle orientation via gyroscopic MEMS sensors, and passenger occupancy and weight sensors to both calculate the severity and kinematics of the impact to determine the appropriate airbags and force and stage systems to deploy. On some vehicles, secondary systems such as pyrotechnic seatbelt tensioners, neck protecting structures, and rollover protection may also be deployed based on the collision profile. Logging of the data involved in the crash event for crash reconstruction purposes may also occur on more contemporary systems. On modern ACUs, this entire identification and response can occur in as little as 2 to 3 milliseconds from initial contact. During the mid-1990s, a less toxic alternative to sodium azide was sought after due to the irritation concerns with its byproducts. Tetrazoles were seen as a promising alternative. Tetrazoles are a relatively stable class of synthetic organic compounds that react in a non-toxic manner to produce primarily water and nitrogen gas. However, it proved to be more costly than sodium azide, with some airbag manufacturers such as Takata abandoning the use of tetrazoles due to cost. By 2000, Takata would adopt a cheaper alternative based on ammonium nitrate, which proved to be a disastrous decision, leading to the eventual recall of airbags in over 34 million vehicles worldwide. It was discovered that the ammonium nitrate-based compounds used by Takata is highly sensitive to temperature changes and absorbs moisture easily, causing it to break down over time. When triggered, the saturated propellant would undergo violent explosions, causing the rupturing of airbags and shrapnel flying towards the passengers. An ultimate solution to this gas-generating problem would be derived from developments made in the late 1970s by chemical engineer Jawaharlal Ramnaresh. Ramnaresh was a propellant expert who had built a reputation for solving munitions design challenges faced by the US military, such as solving the propellant issues that caused early reliability issues with the M16 rifle. He would be tasked with developing a more refined, cooler-reacting, smokeless gas generator start cartridge for starting turbine engines in the field. Ramnaresh had proposed a castable system made from guanidine nitrate that not only had a high gas output and low flame temperature, but also produced inert water, nitrogen, and carbon in its reaction. Fast forward 3 decades, and the properties of guanidine nitrate would show up once again, becoming the ideal alternative to the existing gas-generating compounds in airbags. It's less toxic than sodium azide, less costly than tetrazoles, and most importantly, vastly more stable and less moisture absorbent than ammonium nitrate. Guanidine nitrate quickly became the ideal choice for the vast majority of airbag systems, becoming the most common gas-generating agent used in airbags today. Currently, the supplemental restraint industry is going through a third wave of development, though now a software revolution. With vehicles now coming standard with 10 airbags and over 25 system-wide sensors, on top of dozens of channels of data available from other vehicle systems, modern airbag control systems have computing power comparable to the average desktop computer from just 10 years ago. These systems have become so sophisticated at crash detection that airbag technology has begun migrating to motorcycles and even being embedded in racing suits. Each manufacturer now competes in a software arms race to produce the safest and most reliable algorithms that will perpetually monitor a vehicle's environment for easily over a decade, until that milliseconds-long window of opportunity to save lives presents itself. It's almost the recurring theme of the 20th century that a great idea like airbags would get its start as an electromechanical device, but then be completely transformed by the digital revolution into a technology with once unimaginable capabilities. Have you ever wanted to build a solid foundation for understanding how algorithms, data analysis, and even AI drive the world around us? That's where Brilliant.org comes in. Brilliant is my go-to tool for diving headfirst into learning a new concept. It's a website and app built off the principle of active problem solving. Because to truly learn something, it takes more than just watching it. You have to experience it. Brilliant is constantly developing their courses to offer the most visual, hands-on approach possible to make mastering the key concepts behind today's technology effective and engaging. One of my personal personal favorites is the Computer Science Essentials courses that allow you to build, examine, and self-discover the critical abstract concepts of coding through the eyes of algorithmic thinking using interactive exercises. With Brilliant, you learn in depth and at your own pace. It's not about memorizing or regurgitating facts. You simply pick a course you're interested in and get started. If you feel stuck or made a mistake, an explanation is always available to help you through the learning process. To try everything Brilliant has to offer free for a full 30 days and start learning STEM today, visit brilliant.org/newmind or click on the link in the description below. The first 200 of you will get 20% off Brilliant's annual premium subscription.